Today we will discuss PV module encapsulation materials. We will start with reviewing the requirements of PV module encapsulation materials. Then we will give a market overview and go into different materials. Let us briefly recap the standard PV module architecture. In it, one encapsulation layer is placed on top of the solar cell matrix, with the cell interconnection ribbons separating it from the front glass, and another layer is placed on the rear of the matrix, separating it from the backsheet or the rear glass. The material used in this encapsulation layer has to fulfill several requirements. Optically, they have to be similar to glass. The difference in refractive indices of the glass and the encapsulation material creates reflection at the interface between them. In the figure, we see the complex part of the refractive index, also called extinction coefficient. A lower extinction coefficient means a lower absorption of the material. If an encapsulation material has high transmittance in the wavelength range between 320 and 1150 nanometers, we call it UV transmitting. The other category is called UV absorbing because it absorbs UV light. Note that the UV absorption is usually caused by additives in the encapsulation material rather than the base material. The UV absorption can be used to protect the surfaces of the solar cell from degradation caused by the high energy UV photons. More on that can be found in the reference literature. Most current PV modules contain solar cells which are stable under UV light. This enables the use of UV transmitting encapsulation, which increases PV module's power output by about 2%, as the UV light can be converted into electrical power. Mechanically, the encapsulation material has to buffer between the cells so they don't break, and additionally it has to provide the adhesion to keep everything in place. Additionally, the encapsulation material has to be an electrical insulator to prevent short circuits, as voltages in a PV system can reach up to 1500 volt. Solar cells heat up during operation, as they are designed as light traps. They are typically the hottest part of a solar module. A higher temperature lowers the operating efficiency and can even cause damage in extreme cases. High thermal conductivity of the encapsulation material helps with passively cooling the solar cells. Encapsulation materials need good long-term stability to minimize reliability issues. Additionally, the cost of the material must be low enough to be competitive with the other encapsulation materials on the market. This slide shows a current market overview and a projection of the next 10 years from the most recent version of the International Technology Roadmap for Photovoltaics. Transparent ethylene vinyl acetate, or EVA, has a market share of over 70%, which is projected to slowly decline to about 50% in 2032. Polyolefin is projected to grow in market share from about 10% today to about 20% in the same time frame. Other material options include a mix of the two and silicone. Due to their dominance in the market, we will focus on the former two in the following. Let's first talk about the most common encapsulation material, EVA. It has been used in PV modules for several decades and improved in quality while reducing in price. The main disadvantage of EVA are in the reliability aspects. In the past, issues with additives causing yellowing or browning have mostly been solved. However, high water vapor transmission continues to contribute to degradation effects such as corrosion of metal contacts. In the past years, susceptibility to potential induced degradation has become the most imminent degradation issue. PV modules with low volume resistivity EVAs can be susceptible to PID. In the figure, we see how the modules with EVA, shown in red, fail the 2-PID test. The polyolefin encapsulated modules, shown in blue, pass these tests due to their higher volume resistivity. It is important to mention that there are other things in a PV module which can be adjusted to reduce PID. Another example besides the encapsulation material are the cell passivation layers. Polyolefin offers other advantages compared to EVA, such as a higher durability of the base material and a lower water vapor transmission rates. This will be especially important for future perovskite solar cells, which degrade more easily than today's silicon solar cells. As polyolefin is laminated in a similar process to EVA, the switch generally does not require different tools. The main disadvantage of polyolefin compared to EVA is the higher material cost. Let us summarize the lecture. First, we discussed the required material properties, from high transmission over mechanical criteria such as buffering and adhesion to electrical insulation, thermal conductivity, high reliability, and low price. Secondly, we saw in the market overview that EVA is used in more than 70% of all PV modules today. Alternatives such as polyolefin offer advantages in terms of reliability due to better PID resistance and lower water indicators. However, these advantages come at a higher material cost.